Hello. Hey.
Hello everyone. Today I and Zera giving you a talk about HAMi and Viettel Cloud. How HAMi go from a project to we apply it into Viettel Cloud in a production level. I am Thế Anh, the software engineer from Viettel Network, and then here is HAMi. Zera.
Hey everyone, this is Reza. I'm with Dynamia. Two of our founders actually created HAMi and then created a company. I'm doing go-to-market and the solution architecture. So real quick about the problem. Basically, traditionally in Kubernetes, you would allocate GPUs atomically. And now, of course, you want to share them. You want to utilize them better. And of course, your first reaction, if you know, is like, why don't you just use DRA? We'll get to that. So basically, if you have, for example, two users, you have one with, say you have a V100, 32 gigs. You have one kind of user that has like PyTorch notebooks, and then the other one running some chatbots, one with 10 gigs and the other with 20. Before, you would just allocate the 4 GPUs, and then after HAMi, you basically pack them neatly, and then you get extra GPUs that you can use. So we don't know exactly how much time we have. So basically, a couple of things that we can derive from that is one is actually among the problems that we know right now coming up is that GPUs are scarce. So like NVIDIA availability is getting harder. Vendor lock-in actually is a problem, but with all the tools that we have is getting better to solve. You have like low utilization. It says 10% here, like 30% here, but it can be as low as like 10 or less. You have no central observability if you have multiple devices, and then like the fragmented workloads. So what do you want? You want like hardware agnostic, you want a single API to run all of them, you want easy like fractional GPUs, and you want advanced scheduling to make sure that they're like scheduled optimally, like high performance and whatever. A good example we have actually from Wafer AI recently. They were working on like CUDA kernel and like LLM kernel optimization, and basically they have a use case where GLM, they ported GLM 5.2, 80% of the B200 performance, but a third of the cost. So you don't want to be dependent just on NVIDIA. So the solution, one of the solutions is DRA. I'm not going to go into this, but basically DRA is not just one thing. DRA is a bunch of different proposals. You can do basic slicing now, but there's more stuff coming like that you need for like topology and like other stuff. Real quick on DRA, basically the driver publishes a resource slice that you can then allocate and claim, very much like when you do like storage claims before. About HAMi. Too fast? Okay. I guess I can slow down a bit. So HAMi, like 6 of the main things that we have is heterogeneous management, so hardware agnostic, like GPUs, MPUs, AWS TPU in there as well, like hard isolation, advanced scheduling, like bin pack spread, topology aware placement, and then of course we support all the APIs. We support DRA also. Actually, we have some features that the NVIDIA driver does not have with DRA. And then you have like standard Kubernetes resource isolation, like namespace-based isolation. You have unified, it's better, monitoring, so you don't have to handle each driver or each GPU separately. So how does it work? For the small slices, for example, basically NVIDIA has a mutating webhook which injects device requests into the pod. The scheduler selects the node and the GPU, and then the device plugin allocates GPU memory or the DAA driver, and then the container runtime injects the HAMi core library, and then the HAMi core enforces isolation and the other things. So just an example, we have 10 plus devices. All of them follow the same user structure. and unlike MIG, which we also support, you can have like slices as small as 1 megabyte for example, computer vision tasks. Scheduling policies, real quick thing everyone should know if they don't know yet. Bin, pack, and spread, where we have like 2 different kinds. One is per node and one is per GPU. If you look at the left, you see the per node, where basically you pack them on a node, and on the right you see that you pack them on the GPUs in that node. Some of the use cases, like high availability, of course that's going to be more expensive. Latency, for example, when you need more performance, you don't want to have, for example, you have a big model, you don't want to share the compute, but you don't actually need as much VRAM, for example, then you have to kind of think about how you want to schedule them. Topology aware, so for example, for training jobs or other things, you might need to select how the GPUs are connected, and one of the ways you do that in some of the CNCF reference architectures is that you actually pin the GPUs. But HAMi supports topology for not just NVIDIA, but also Ascend and like some other things. And just as a reference, for example, you see like PCIe 5, 128 gigs, max 6, 242, but then if you look at NVLink, already like the 4, we're at 6 now, is like 600 gigs. It's like for many people that are on 5 still, like 5 times as much, and then it just goes down that way. But I don't think you need a Rubin for most things. Common question that people ask is, okay, I already have MIG, why do I need HAMi? Or like, there's now DRA, why do I need HAMi? Several points I already made. HAMi supports both MIG and non-MIG. If you do MIG, HAMi does dynamic MIG profile. So you don't have to first load your MIG profile. HAMi does it for you. And then actually, if you change your workload and the node is empty, it can actually repartition the MIG without you having to do it manually. And then for DRA, as I mentioned earlier, when you saw that big table of the caps that we have about DRA, we are actually not there yet where you can just do advanced scheduling with just DRA. But even then, I think some things will move into the DRA layer, but then you will still have other supporting technologies. So not only do we support you like to experiment and like use DRA if you need to, or for example, you have a unicorn task that you want to run and you want to run HAMi with it, then you can just use the HAMi DRA driver. But I think it's a journey where HAMi is also contributing. And with that,
yeah, is the part 3 of Viettel Cloud, what we measure, what broke, and what we learned after a time we using HAMi. And who we are, I am Thế Anh, you already know. And Viettel Cloud is the cloud platform of Viettel Group, Vietnam's largest telco. And in Viettel Cloud, we have Viettel Cloud AI Native. It's about the AI GPU platform. And we also provide the AI notebooks with fractional GPU with built-in HAMi inside. We use it for dev and training. And also, in this talk, I will give you some metrics about the inference serving using HAMi. We have currently we have 2 pools at 200 with 141 gigabyte VRAM plus L40, L48, etc. And we are in the world now. They have 51 platform has the certified Kubernetes AI platform, and we are the first and only in Vietnam have it, the 20 worldwide. What we run today is HAMi in our cluster is the latest version to 2.9 in both clusters, the H200 pool and the mixed GPU one, and our own every engineer use it every day. The memory limit we see is real. The port see only 2 gigabytes if you set the limit for the GPU mem. Yeah, and in the cluster, HAMi lives next to the Slinky system on Kubernetes inference, and we have also KDA for autoscale. We have full monitoring. The default of the DCGM exporter from NVIDIA, we can only see the host level metrics. With HAMi, we can see down to per pod GPU metrics. That's very nice from HAMi. The user only needs to write the format that Zera showed you guys already. And our researcher even not to do it manually. They pick in the UI of the AI notebook. We built it on Kubeflow notebook. The number in this talk is mostly from 200, H200 pool and a few from L40. The next we have the problem we measure. We have here 2 real jobs that we are running. The first one is you can see the time series for the inference. It's based on the Kronos model. It's about 200 million parameters, so it's only used about more than 1 gig VRAM. The streaming multiprocessor use only 16 to 18% of the whole H200 card. Yeah, we can see that the time series job left the whole H200 free and about 80% of the GPU doing nothing. And the second one, we have the defect detection. This job is the YOLO job that we use only about almost 40 gigabyte of RAM use. And you guys can see we have the 100 gigabyte VRAM free. We can use this for inference. We can use it for more notebooks. We can use it for computer vision or embedding jobs. And the detection took only 39 gigabyte of VRAM because we use it for purpose, not for why only 39. And remember that H200 has mic, but many of our GPUs have no mic at all. L40 at A6000. And the default of Kubernetes gives you one choice, NVIDIA.com GPU1 and the whole card or nothing. The result for this is for the inference time series job. We can got more than 3 times per GPU. That this job we fixed the SLA to P95 to 160 milliseconds per GPU. We use it for with the native job. We see that it's only the request per second. We can only see we can only get 20.7 requests per second. But with HAMi, we use it with CADA for auto scale. Within the same GPU card, we can get more than 3 times the request per second. That we fix the SLA millisecond. But even we try to fix didn't fix the SLA. It only can get about, I think, almost 30 requests per second. Cannot do more. You guys can see the right chart is the streaming multiprocessor utilization. When we increase the rapid card for the inference time series jobs, you can see the utilization of the card can reach about 100%. Yeah, with the same latency. Yeah, but this proves that with HAMi and CADA for auto scale, we can use for more than 3 times work per GPU. But HAMi does not make one pod faster. It fills the GPU that was sitting empty. Yeah, and some metrics we can see that because of 1 GPU instead of 3.4, so 71 fewer costs. The power is almost a half, and we can save that about 7,000 per month. An example of the GPU H200 about $4 per hour. And yeah, one day we proved that we have a workload with AI training. The second job that we use for the training is YOLO 11. with about a lot of image in bus size 64. So that's why only 39 gigabyte of RAM used. The bus is sized for the accuracy, not for. Some people may ask, maybe we can increase it to 512, but yeah, the bus size for this job is only need 64, not to fill the cut. So we have almost 100 gigabyte of RAM is generally free, not for just idle. But we pay the price for it because we find 30% and cap the notebook at only about 70% of the core. So the notebook see only its out slice. It cannot out memory for the neighbors, and the core are capped. So we can use the rest for other jobs. The price with this model we pay about 20 minutes. It on purpose. The price is only for small model one, but the bigger one would cost more. Yeah, but this price, I think we can agree with that. Yeah, the rest follow the load because we fix the training job on notebook fixed all day. The rest we can use about 70% of the code, means 100 gigabyte of VRAM we can use for inference or more training. The chart is about the time I let it there is, for example, in the morning, everyone come to the office and they get the time series inference. They get on the load of the infrastructure. The time series is for detect the inference, for check the load of the infrastructure, the CPU, the network, and yeah, it can use for scale up to 6 times. But in the office hour, when you have all the load from the time series model, we can use it for the data for our inference. We can scale up to 5 times, and at the night we can, with inference is lower than we can use the memory, the core for more training. Yeah, because of the time series is about it bursty depends on the time. So that means even it with one card we can never let it idle. Yeah. So yeah, with HAMi it's very useful for that. But yeah, HAMi does not always have. It depends on the use case that we use. It have when the code is empty and the job is about the behavior is small and bursty, like the inference take only 18% of the streaming multiprocessor. The code is about almost 80% idle. So we pack it about 10 replica. So the utilization hits 100%. So that's why with one card we can do more than 3 times work. But some case HAMi will not fit, like training with big LLM with one instance already started the whole code. Like with the big LLM, we will measure that with one replica, it can get about the token per second about 12K. But for small one in the same code cannot get about 12K. We only add more than 7K with the same training job. Yeah, even we have the packing loose for that. When we scale up to 4 replicas, big and yeah. With HAMi, careful for what you promise the user. The default one, the GPU memory is a real limit, and your neighbor is safe. It means that other jobs cannot be our memory with the GPU core default one on a hint. You give it 10% or 90% run the same speed, but if you get it, let it the Fox one, it's a real cap. That's what we do. 70% cost take more than 1 hour, not 1 hour. What it really took is the hard part is not install HAMi. Install HAMi is very easy with HAMi install, but we have some obstacle like the HAMi's privilege access conflict with Kubernetes policy. We have the solution here. We just need to exclude the HAMi system namespace from post security policy, and with the default operator of NVIDIA and HAMi, we need to turn off the device plugin of the operator and turn off the CDI. The resource pool overlap. With one cluster, we have some case like we want to have some nodes for fraction. We have some node for full GPU. We have some node for slum jobs. We use Slinky in the Kubernetes. Yeah, the solution just simple. Use our pool, our scheduler, and tell nodes for the purpose. And with the latest version of HAMi 2.9 metric, it's a refactor. The dashboard Grafana may mismatch. Yeah, use the prefix HAMi, but we fix it and we even contribute to the upstream already. Yeah, remember that HAMi is an operation project, not one line install. So yeah, sometimes it can be hard. And where the magic breaks, HAMi, the mechanism of HAMi is sit in front of every CUDA that Zera showed you guys already. And in some cases, if you go around CUDA, the HAMi cannot see you. Like the ARP framework, when use CUDA, I think on most of the AI job is CUDA, but yeah, something like the image, the container images from NumPy or MGSL, yeah, it does not have the lib DL, so it will be break. The solution is use a glibc CUDA image based from Debian or Ubuntu. The runtime of MATLAB, yeah, MATLAB freeze before it even reach CUDA code, so yeah, keep in mind that it will not work with MATLAB. But the nice is HAMi works very well with even multi-GPU. We see the GPU peer-to-peer, we test it peer-to-peer on reduce, tensor parallel, and on CUDA graph on Nickel, yeah, on stay inside CUDA and on works very well. And what is next for us? So I think next year we want to have more teams inside Viettel with quota per team, more pools, yeah, the rest of the fleet and more workload tie on the same card agent, bigger LLMs, batch jobs, move to DRA like Zera. So, yeah.
So real quick, where we are today, we have 7 case studies on the CNCF website right now. You can go check them out, and then some different metrics like TX GPU density. I didn't write which one it is. Like workloads per device, like less ops. Depending on what people are looking into. So case studies, I think actually the GitHub stars is more, it's like probably 5,000 according to the Linux Foundation. You can use it with like Volcano, Q, Coordinator, Kai Scheduler is also integrated, like device support, don't know if it's up to date, a lot more adopters than we have here. So you can check the HAMi website, and then if you have questions, if you want to scan that, the slides and some stuff is over there.
Oh,